I am an astrophysicist, and my research is about taking data using telescopes and put data in computers, and then get some numbers that describes our universe. For example, our universe is known to be about 13.797 plus or minus 0.023 years. And today I actually get a chance to talk about how we actually do it. I often said this is a huge error propagation problem, but how exactly we do it? We use galaxies to study our universe. This is a picture of the Andromeda galaxy, very similar to our Milky Way. It has about 100 billion stars in it. Each star is similar or bigger to our sun. And I use millions of galaxies and perhaps billions with a new experiment. So here is a picture of the distant universe and taken by the Hubble Space Telescope. Each point here is a galaxy, similar or bigger or smaller to our Milky Way galaxy. And the goal of our experiment is to look for all these galaxies in the entire sky or in the entire universe. Here's one example. Here is a map of the sky projected on an oval, just like the world map can be projected on an oval. And each point is the location of a galaxy in the sky. And the color indicates how far away they are from us. And this experiment is really only scans the nearby universe. And our new experiment is going to look for farther and farther away galaxies across the entire sky. Our universe is determined by numbers. Some of you might have heard about this book called Just 6 Numbers by Martin Rees. There he argues that, or he describes that our universe and actually life and everything is shaped by these 6 numbers. So epsilon, the binding strength of atomic nuclei, determines how elements are made. (42) And sorry, I don't get a 42. Can you explain to me?
Sorry, it's a reference to the Hitchhiker's Guide to the Galaxy.
Oh, yes, now I remember. Yes, I should bring a towel next time too. Yeah.
Well, it was 47.
42, 21 is just half of the truth.
Yes. Yeah. Sorry. Yeah, and also the strength of electric field versus gravity rules, obviously, and the total matter density, total dark energy density in the universe, and density fluctuations, or you can think of like the mean densities and the standard deviations of density fluctuations, and finally space dimensions 3. So well, not all these parameters are really cosmological. Actually, 3 and 4 and 5 are actually the parameters we are pursuing in cosmology. So there I mentioned dark energy and dark matter. Now we have overwhelming evidence that our universe has these 2 weird components. I won't get a chance to talk about how they were discovered because I'm going to talk about the computing components more, but just take my word for it. So our universe is expanding, and it's expanding faster and faster. And the explanation is that our universe has, or is dominated by this strange component called dark energy. It has a very strange equation of state, or it has sort of like negative pressure, making our universe expand faster and faster. And another important component is dark matter. We have found that, or we have very strong evidence that most of the matter in the universe doesn't emit light, doesn't interact doesn't involve in electromagnetic interactions. They only interact through gravity. So we call them dark matter. They have to be there, otherwise structures cannot form, galaxies cannot form. And finally, the ordinary matter, the elements on periodic table and the gas and galaxies is only about 5% of the universe. And so what we can see using our telescopes is only this 5%, the ordinary matter, gas and galaxies. And this talk and or my entire research is all about using what we can see to infer the parameters that describes dark matter and dark energy. So as I mentioned, that we have big experiments measuring several parameters, and we have several very strange symbols. So don't worry about them, but I just want to mention that the few key parameters we are measuring with our experiments include the expansion rate of the universe, the matter density, dark energy density, and this funny looking called sigma 8, basically the density fluctuations. So I mentioned that this is basically like standard deviation, or the matter density is like mean, and sigma 8 is like standard deviation. So to explain this sigma 8, we can imagine here, this picture is the density field in the universe simulated. And you can see the high density region that's brighter and low density region that's darker. And then we can draw spheres on this density field. For example, if we draw a sphere here centered on high density region, this circle will have a high average density. And if we draw a sphere here in the hollow region, we will have a low density. So we can draw many of these spheres, and then we calculate the standard deviation of the density in these spheres. And that's the meaning of this sigma 8 parameters. This is actually one of the most important parameters in cosmology. And just in case you are interested, this is the parameter measurement that we have today, taken from the particle data group, just in case you are interested in the best experimental results we have for now. And it's perhaps a little bit embarrassing that we actually don't know how fast our universe is actually expanding, because the measurement for like expansion rate actually disagrees quite a bit. And these different points shows that the expansion rate, some experiments indicate that the expansion rate or this H0 value is around 67. And some experiments indicate it's around 73. And these are different, using different method that relies on different physics. So in this talk, I will also talk about how do we decide whether these are indeed intention. When can we roll out our models? And of course, all these parameters, they can be degenerate with each other. They degenerate with each other, meaning that some combination of these parameters can give you the same observational results. You can't distinguish several combinations of parameters. And these contours just indicate the parameter degeneracy. So here we are measuring matter density and the density fluctuations, like the one I say, draw the spheres and calculate the standard deviation. For example, maybe it's easier to look at the red one. So you can see that the value here, higher value in both or lower value in both are both accepted by this experiment represented by red. And these different experiments are sensitive to these parameters in different ways. So their degeneracy, their contour, shape, and direction is different. And as I mentioned, that one of the questions is actually to quantify whether these are consistent or they are intention. So I mentioned that my experiment or my research is actually going from pictures of billions, we don't have billions yet, we have a few tens or 100 millions of galaxies, and we go to, and we obtain the constraints parameters. How do we do that? So first, we will obtain some summary statistics from the galaxies we look in the sky. And they are, I will focus on correlation functions. There are other summary statistics. And then I will talk about how we model the universe, which involves running lots of simulations and interpolate the results from this experiment or simulations. And then to get this kind of contour, we are inferring parameters, or basically the big error propagation part. And then we will use Markov chain Monte Carlo, and I will talk about those. And finally, how do we compare different experiments and whether they are intention or they are consistent. So let's first talk about the summary statistics we use. Actually, I forgot to mention, all of you are welcome to ask questions, ask for clarifications, or interrupt, or send jokes in the chat. I will appreciate that very, very much. And so I show this. We basically look at galaxy distribution on the sky. And the first thing is to actually extract some statistics from this kind of map of galaxy locations. And the most obvious thing is to see how many there are and how many there are in a unit area or unit volume of our universe, or number or density of objects. It's easy, just count. So the fancy way to call it is actually 1-point statistics, in contrast to 2-point statistics. There, we, instead of counting objects themselves, we count number of pairs. So there are one pair that separates 1 degree in the sky, and there are like 10 pairs that separates like 2 degrees in the sky, that kind of calculation. So count pairs as a function of distances. And what this is telling us is that there's this clustering as a function of scales. If there are, for example, if we see lots of pairs, they are separated by 10 degrees on the sky, we know there's some interesting scales, or there's some interesting physics associated with that particular scale. And we also call this 2-point correlation function. And its Fourier transform is called power spectrum. You might have heard of it. So it's for so correlation function and power spectrum are some of the most powerful summary statistics we are using in cosmology. And of course, we can keep going. Instead, we can do 3-point statistics. Instead of pairs, now we have 3 trios or triplets of galaxies. And now it's more complicated because if it's 3 galaxies, it forms a triangle. And we need to take into account the configuration of the triangle, whether it's equilateral triangle and the length of equilateral triangle and or squeeze the triangle, or yeah. So there are lots of possibilities with 3-point statistics, which is still there's still lots of it's still new. It's not widely as used as 2-point statistics, but there are lots of research going on with 3-point statistics as well. So
can I ask a quick question?
Yes.
When you think, so when you have this data and you literally think of these galaxies as existing at a point in space, they don't have any extent, like it's not like a disk or something.
Right. Basically, yes. So we basically, well, in physics we say there are test particles. We just assume they are just points probing the density field in the sky.
Okay.
Yes, exactly. But So there's always a but. So, but galaxies, some of them are bright, some of them are dim, some of them look bluer, some of them look redder, meaning they have different kind of stars in them. They have different formation, or they have different astrophysics going on in them. And sometimes we do need to take into those account. So they are no longer points. Like we call it marked statistics. Like the point themselves actually carry a label or a mark with them.
So they're real, but for what you're talking about, they're kind of like just mathematical points without any attributes, no weight, no mass, no.
Yeah, exactly. So for this, that's basically how we use galaxies. Mm-hmm. Yeah, or at least in this talk. And right. As I mentioned, we can add their color. It's most commonly to just brightness and colors if we want to do this marked statistics thing.
Okay, cool.
Yeah, great question. Thank you so much, Donna. Well, actually, if any of you use this similar thing or similar method I'm using, I'd really love to know. Or if it's actually said anything wrong, because, like either in math or statistics, I'd love to know as well. So 2-point correlation function. So this is again projected area. Projected sky, and here are the locations of the massive galaxies. And here is the location or distribution of the low mass galaxies. So you can see that there are fewer high mass galaxies, and there are more low mass galaxies. So in terms of 1-point statistics or density, low mass galaxies have higher density. But we can also look at its correlation function. So it turns out that high mass galaxies, although they are more rare, they tend to appear close to each other. So one analogy we have here is that we often use is that high mountains, like very tall mountains above 14,000 feet mountains, they are rare, but they are all clustered together. For example, you probably know that the 10 tallest mountains in the United States are in Alaska. I think probably, I think 13 out of 15 of the tallest mountains are in Alaska. They are all like in a small region. So it's the same thing here. So most high mass galaxies, bigger galaxies, they form in near each other. And to quantify this, we calculate correlation functions. So I mentioned correlation functions are basically number of pairs as a function of distances. And of course, for number of pairs, it's affected by the volume. So we divide that with respect to the random distribution to take into account the effect of volume. So if we have a random distribution in this, we will have a flat correlation function. And the high mass and low mass galaxies, turns out their correlation function to a lowest order appears like a power law. And the height or the amplitude of the correlation function is determined by the sigma 8 parameter, or the parameter describing the density fluctuations in our universe, and also their galaxy mass. So the thing we do is, so you can see there's degeneracy here between sigma 8 and galaxy mass. We need to measure galaxies using different samples and different cross correlations to actually break the degeneracy between sigma 8 and more astrophysical parameters. And to calculate correlation function, we use this algorithm. It's probably very commonly used in many fields, KD tree, or it's Kdimensional tree. So we have a bunch of points, and then we want to calculate the distances between points, like all pairs of points. So if we have 1 million galaxies, we can't just do pair by pair. It's impossible to do that. So a common way is to first divide the points in one dimension into two halves, and then kind of two leaves, and then two leaves of the tree. And then in another dimension, we further divide the points. So we usually divide them so that each cells have equal amount of density. And then each steps, you have orthogonal direction in dividing or in generating newer leaves. Then we keep going. And when we need to count the pairs of a given distance, we only need to look for the cells that are within that distance. For example, if we want to calculate the distance, the pairs that's within two cells, then we can just take into account the nearby cells without going into the entire sample. So that's a way to speed up the correlation function or pair counting calculations. And they are also speed up for this procedure and matching the software architecture. And then some of the examples are cited here. And the core fund is the code that in one of the fastest one in our field that incorporate the hardware aspects. So I like to talk further about cross-correlation. Yes, exactly. So these are 2D pictures, but are the data actually in 3D? Yes. So actually, sometimes if we have, so it's a great question. So in astronomy, we need to measure distances in order to know the third dimension. So if we look at the sky, everything is 2D. We need a distance to measure the third dimension. So if we have very good distance measurements, which is actually very hard and expensive, we can do 3D calculations. But in astronomy, a lot of time we only to do 2D calculations. Great question, thank you. So yes, I like to talk about cross-correlation. But before I talk about that, please allow me to talk a little bit astrophysics. So my research is about galaxy clusters. And here is a picture of a galaxy cluster taken by the Hubble Space Telescope. You can see these orange blobs. These are basically the big galaxies inside the galaxy cluster. And they are the highest density peaks, or they are tallest mountains in the universe. And their mass is about 10 to the 14 to 10 to the 15 times of our sun. So, but this mass is mostly in the form of dark matter. We can't see them directly by telescopes, but we infer them, which I'll talk about that in a bit. And their sizes are a few million light years across. So to put things in aspects, the Milky Way size is about 10 to the 11 solar mass, and its size is about 50,000 light years. So this is like really 1,000 times bigger than our Milky Way, this kind of structure. And when there is mass, there is, how do we know there are clusters? Could it be the angle we are looking at? Could they be far apart in the third dimension? Don't know. This is exactly what I'm worrying about every day in my research. A lot of my research is about, is my cluster sample, how pure are they? Are they really, are they really like physically in a small region, or are they just like, or are they just a bunch of things happen to be in the same location on the sky? So the best way to determine that is if we know the distance of all these galaxies. Yeah, we know they are physically together in the sky. So that's when, if we have very good measurement of distances.
So you know the distance in the third direction.
Yeah. So that would be the best way to
view. Suddenly they might appear far apart. I see.
Yeah. So that is when we have good distance measurements for galaxies. But distance measurement, as I said, requires a lot of telescope time to take spectra or other measurements. So sometimes we just don't have very good distance measurement for them. So we have to make a guess. Maybe not 10% of them are contaminants, maybe, yeah, that kind of, yeah, and then that falls into our systematic error as well. Yeah, great question. Thank you, Donna. I would never have the chance to bring up the things I worry about every day in my research. So this thing has lots of mass. Our gas clusters has 10 to the 15 solar mass in them. So we know that gravity mass bends light, or gravity bends light. So you probably have seen this gravitational lensing or story that first how general relativity was first verified through observations of gravitational lensing. So here's the sun, and it distorts space-time, and the path of the light will follow the shortest distance in this distorted space-time before it reaches the Earth. So it looks as if the light is bent in space. And when we look at the star, it looks as if the location of the star is shifted. So this effect happens to galaxy clusters as well, and to a bigger scale. So here, instead of the sun, we have the galaxy cluster. Instead of a distant star, we have a galaxy which has many stars. So you can, like these stars emit light in all directions, and then they also go through their shortest distance in this distorted space-time to the Earth. So you can imagine that in this galaxy, like the location of every star is shifted a little by gravitational lensing. So the net effect is that the entire shape of this galaxy is distorted. So here is the same galaxy cluster, and you can see there are these arcs in this image. These are actually the gravitational lensing effect. These are distant galaxies, and their shapes are distorted by the gravity, by the matter inside the cluster. So by the distorted shape, we can infer how much matter there is inside this cluster. And then we infer that there are much more mass than there is inside its galaxies. So that's one of the strong evidence of dark matter, that this gravitational lensing indicates there has to exist matter that we cannot detect by photons or electromagnetic waves. So here is a cartoon picture. So let's just assume all the galaxies in the universe are round circles. And if we put a galaxy cluster in front of it, and then they will all be distorted due to the gravitational lensing effect. So you can see that there is this spherical patterns. So when we see there's spherical patterns, we can indicate that there's a large chunk of mass there. And then we can use that to infer how much dark matter there is. So I was just talking about correlation function. What does it have to do with this? This is actually a correlation function problem. We are basically calculating the correlation between galaxy clusters and the galaxy ellipticities. So here you can see that there's here galaxy clusters introduce these ellipticities. So you can see a strong correlation at this distance between galaxy ellipticities and the galaxy clusters position. So such a correlation function, cross-correlation function, actually tells us about where dark matter is in the universe, their fluctuations, their distributions. Any questions about the correlation function and gravitational lensing before I move on to modeling?
Actually, I have one quick question. I'm just curious, is there, sort of get back to this third dimension idea,
Yeah.
What is there, is the fact that we can see these things mean that they all exist in kind of a shallow, like they're all, the distances from us is roughly, is much smaller than, say, the horizontal vertical extent, I guess. I mean,
yeah, so yeah, maybe this one will help. So yeah, this one is definitely not to scale, but so this this galaxy cluster is usually 1 arc minute in the sky. So 1 arc minute is 1/60th of a degree, and the moon is half a degree. And well, sorry, that's not a good description. So let me just use the physical distance. So this galaxy cluster, its size is about 1 million light year, maybe 3 million light years, but give or take. Yeah, but this distance is about 1 billion light years, or half a billion light years, give or take. So the distance between Earth and the distance between the faraway galaxy, this distance is basically in the order of billion light years, and yeah, this cluster is about million light years. So it's so yeah, actually this is,
it's quite, so we have quite deep visual.
Yes.
Yeah. Okay. I got. I don't. Okay.
Yeah, this is actually great. I didn't it's like I didn't realize that it's not. Yeah, this figures awfully off scale. It's maybe really confusing.
Well, this is when you talk about lensing, there's like a big hole, but I would have thought that we would see things, even if it's a spherical lens, it's not we would see things behind it, and then it would be hard to detect a lens if, it's really just like a hole in the universe, because we would see everything coming, that we're behind the lens, but maybe I'm not.
Yeah, actually, what we are really doing is that we basically we have some rough estimate about how the distance of these galaxies, and we look at them. If they look unusually elliptical, or they look as if they look unusually sheared, or we call them they have unusual ellipticities, and we know that they have gravitational lensing effect. And we basically do that statistically. We rarely do that case by case. We have an entire sky of galaxies, and then they also have some ellipticities. And then we have another map of galaxy clusters, and we cross-correlate them. So yeah, so we are so it's this cartoon picture, so kind of misleading. We are not really looking at patterns like this. We basically look for the distortions or the ellipticity of the galaxies on the entire sky, and through this statistical method, cross-correlation approach, that we can infer like how mass is distributed inside clusters.
Okay. Keep going. Sorry.
Yeah, well, this is great. Yeah, because this is like, yeah. And this is my first time explaining this in this computational method context. And yeah, I'm so glad that you asked this. And we have one question from Scott. So the unlensed image is what is actually observed, and the lensed image is created by analyzing any spherical pattern that are observed in the unlensed image. Actually, what we observe is lensed image. So the unlensed, this is just for a cartoon illustration. So of course in simulation we will do unlensed and then lensed then first, but in observation what we have is a lensed image. Yeah, and what we do is to use this lensed image to back out the mass distribution that's causing these ellipticities. Does that answer Scott's question? Hey, thank you, Scott. So now we can I might not get to comparing experiments, but that's okay, we'll see. So now, how do we model our universe? As I mentioned, that our universe is determined by numbers. Basically, if we pick a set of numbers, we pick a set of, okay, how much dark energy, how much dark matter, how fast this universe is expanding, we can simulate a universe. And here is an example. Here is a simulation of a galaxy cluster that I did actually for my PhD thesis. So I start with small density fluctuations. So this is the so-called Mbody simulation. We simulate the density field in the universe. And the density field is discretized and using, we call them particles, and to represent the density field of the universe. And we basically calculate the interactions between these particles that represent some mass. So we start with small density fluctuations that's matching the observation of the early universe. And these small fluctuations are amplified by gravity. And then these high bright regions correspond to the high density regions where galaxies form. And you can see that galaxies, they orbit each other due to gravity, and then they sometimes just merge their mass together, and then form bigger galaxies. And at the end, this system is about 10 to the 15 solar mass, and then it has all these galaxies, and then correspond to what we see in the observation. In this simulation, I only take into account gravitational interactions. And so this is, and I assume all the matter here is dark matter because they are the majority anyways. So we can really observe dark matter distributions. We can't really see dark matter by eye, but it's by using galaxies that lives inside these high density regions, we can map them out. We can map out the location of a galaxy cluster, and using the gravitational lensing effect I mentioned, then we can map out the density. So as I mentioned, that we can choose a set of parameters and then choose a initial condition of our universe, and then we can just evolve it. So here I'm showing two examples of the universe simulated using different cosmological models. What was the time period of that simulation? It's, well, our universe is 13.7 billion. I don't remember exactly. I think this is about around 10 billion years. The entire simulation is around a 10 billion year scale. Yes, so the top set of simulation is we assume 30% dark matter and 70% dark energy. And the bottom, we assume 100% dark matter. And you can see that in these two universes, the density field evolves quite differently. And the one with dark energy, and then the density field actually doesn't evolve very much. You can see the same structure, for example, this galaxy here and here and here. And with 100% dark matter, is actually a lot of evolution or a lot of difference between simulations. So, or between time steps. So what we do is that we run this type of simulation and then compare with our sky and see which set of parameters agrees better with our observed universe, and which I'll later talk about how we actually interpolate different simulations. And let me just talk briefly about how these simulations are done. So this is, again, we have particles and maybe a billion particles. We want to calculate the gravitational interactions between all pairs of particles. Again, this is not feasible to do pair by pair calculation. So now we again have a tree algorithm. So again, we divide the entire volume into hierarchical cells. And then we just count, for example, if we want to know the interaction between this cell and this cell, because they are far apart enough that we can only just consider all matter in the cell concentrated in the center of mass. And we can just consider the center of mass interaction between the two cells when they are far apart enough. And this is the most basic algorithm, most common one. And also there's particle mesh algorithms. It's dividing the space into regular grid and then calculate the density or interpolate the density on the grid, and then solve Poisson equation in Fourier space, which is a lot easier to solve. And then we go back to the real space and evolve our density field, and then go to next step. And this is accurate for large scales. Well, as accurate as the grid size we set to that simulation. And an improvement on this algorithm is called particle mesh. So to improve the small scale accuracy, we actually count pair by pair in small scales. These are just simulating gravity, but of course there are also simulations involving hydrodynamics, which I actually won't get to talk about this today. And Mbody simulations, these algorithms are cheap or computationally pretty fast. We can simulate a large volume of our universe using this technique. So this is still basically the most of the cosmology analysis still relies on Mbody simulations, like some combinations of these algorithms. So as I mentioned, we have choices of cosmological parameters. For example, there are probably 10 parameters that decide how the universe evolves, and we want to simulate them we basically want to simulate many of them that spans all the reasonably possible universe. So we need to simulate a wide range of a high dimensional parameter space, and we want to interpolate them. So here are 8 parameters that describes the universe. They are slightly different, matter density, sigma 8, and so on. So how do we decide which parameter to pick? And what has been widely used in cosmology is this so-called Latin hypercube to select the parameters. And we often use the Gaussian process regression to interpolate the results. So we basically every point on this plot correspond to a simulation I just showed. And then after evolving the simulation, we can calculate some summary statistics, and then we use Gaussian process regression to interpolate them. So how do we sample the parameter space? We use this method called Latin hypercube. So the idea is simple, actually. So here is an example of a 3-dimensional parameter space and projected in 3 directions. So the idea is basically only one sampling point can exist in each row and each column. So you can see that we put this parameter in grids, and then each row, each column, there's only one sample point in all dimensions. So if you play chess, or if, like me, you watch Queen's Gambit over the spring break, and this is like if you have 27 rooks or castles, rooks go up and down and left and right to take other pieces. This is like having 27 rooks in peace with each other. So there are more than one solution for this. And another thing to consider is to have an orthogonal array, meaning that the subspace is evenly sampled. This is illustrated using the lower left corner. So you can see that it's homogeneously sampled in each cell, and then there's only one sample point in each projection. So it's not a grid, it's just one sample point in each of the cell. So combine these two, hyperlighting cube and orthogonal array, we can have an even coverage of the parameter space, or basically we have most of the possibilities in the universe simulated, and no points lie on top of each other in any of the projection. So now we, after simulate, for example, 100 universe, we need to interpolate them. So the most one of the most popular way we use is the so-called Gaussian process regression. So it's basically the way to interpolate the summary statistics in this high dimension space. And so here I'm only just using a one dimensions to illustrate the idea. So the interpolation, so here these points of marked with plus signs are basically the training points of this example. This is the first panel is how these points are generated. And then we can set a parameter to tune how the interpolation goes through these points, how squiggly the interpolation functions are. So we have a size dimension in the interpolation kernel. If this hyperparameter L is small, meaning that, and then the curve will be more squiggly. And although we go through all points, when we are away from these training points, the uncertainties will be big. But we still go through all the points. So this is the trade-off using a small or narrower kernel. And then if we use a wider kernel, then we don't go through all the points, but at each point, the uncertainty is relatively small. And this, of course, needs some trial and error, choosing hyperparameters to interpolate the summary statistics among the different cosmological models. And this method has become really popular in astrophysics. It's probably due to this Rasmussen-Williams book, which is free and readable to Muggle astronomers like me. And then we also have a nice Python package called George, and it's very easy to use. So I think I only have 10 minutes left. Maybe we'll skip the last bit, so now we go on to parameter inferences. Now we have our model that interpolate a lot of parameter space. So you can imagine we have a function, which is a big black box, and then you put in parameters in them. You can predict summary statistics in our universe. And then how do we use that to infer parameters? So it's a model fitting problem. So just to make sure we are on the same page here. So we calculate the posterior distribution. So here D is data, or the summary statistics correlation function we observed, and H is hypothesis model. Our universe has dark matter and dark energy, and governed by general relativity. And the posterior is the PDF for the model parameter. And it's a combination of likelihood and prior, and divide by this Bayesian evidence. Well, Bayesian evidence is usually just a normalization parameter, but I'll talk a little bit later that we can use that to select models. or compare different models. So we want to calculate the posterior function. So one of the most, we use Markov chain Monte Carlo, and one of the most popular choice, maybe many of you, some of you might have taught this, the Metropolis-Hastings algorithm to sample the posterior. So we basically have a bunch of points, and then we, at each location, we will propose the next step to go. And where to go next is determined by the posterior in the next step. And probably some possibility to go to a lower so to go to a place where the posterior is lower. So in the end, we will have more sample points where the posterior is high. So this is basically a Monte Carlo calculation for the posterior distribution. And so it can be sometimes be inefficient in sampling parameter space or likelihood function that has islands and or highly degenerate in some directions. So a more popular choice in cosmology now is so-called multinest sampling. So the idea, this is no longer, this is actually sampling parameter space, not generating, this is actually sampling the parameter space and calculate the posterior in different locations. So the idea is that we start with n live points. We draw n live points from the prior, and then we calculate the posterior. We drop the point with the lowest posterior and replace that with another one with higher posterior. And if we go that, we are basically going from the lower, the contour with lower posterior, and then we go to places with higher and higher posterior if we keep doing this. That's the idea of nested sampling. And another very efficient way to do this is the so-called multinest method. So we actually put down light points in ellipsoids in high dimension. So then this is efficient if our contour ends up look like a banana shape or have several islands. And these light points living in ellipsoids will very efficiently sample the very degenerate locations or multiple local maxima. And finally, using these methods, we can have a contour for our parameter constraints. So we want to compare experiments, whether they actually give us the same answer. Sorry, I'm looking at how much time. Okay, 4 minutes. I think I can try to do that. So we have, for example, if we have two experiments, as I mentioned there, we've been measuring the expansion rate using using objects that's closer to us and far away from us. So we want to ask, are the two experiments in tension? And if yes, it could indicate systematic errors that we haven't taken into account in either or both experiments. Or it could indicate that our underlying assumption for fitting these experiments are wrong. So it's always a billion-dollar question. Is my experiment wrong or is Einstein wrong? So to do this, we often use Bayesian. I'm just going to mention three methods that we've been using in cosmology: Bayesian evidence ratios, posterior parameter differences, and posterior predictive distributions. So Bayes evidence ratios, I mentioned Bayes evidence when I show the Bayes theorem, but it's basically integrating likelihood multiplied by prior over the parameter space. So this is very often used for testing hypotheses or comparing two different hypotheses, which one is more likely than the other. So the null hypothesis is that one common set of parameters describe all the data sets. So the data sets are generated from the same underlying parameters and underlying model. And then Then the other hypothesis is that there exists more than one parameters that is described as different data sets. So different data sets are actually generated from different underlying parameters. We can calculate the Bayes ratio. So if the Bayes ratio is less than 1, then indicates there's tension between these two experiments. Or we can use Jeffrey's scale for the Bayes evidence ratio comparison. And the paper I'm citing here are not comprehensive. They are just the examples that people have been using in cosmology. And another method is to compare the posteriors directly. So we have two posteriors, P1 from experiment 1 and P2 from experiment 2. And then we can draw samples, X1 from P1 and X2 from P2. So if we are doing Metropolis Hastings, then we have those automatically. And then we calculate difference between all pairs. We call it lowercase delta. And we basically look at the distribution PDF of this delta. So then here is, for example, if our PDF looks like this, and here is 0, we exclude the, or we calculate the area that's in this blue shaded region with probability lower than this point, and also this point, and then this region. So we integrate the area. So that's our p-value. So the probability that the two distributions are the same is by integrating these blue areas, or mathematically, when the probability is less than the probability at 0. So we can see that if the difference is small, then the p-value will be big, and that means that our experiment, the two posteriors are consistent with each other. And one last method that I like to mention is the posterior predictive distribution. So for a given observed data set, we call it D-obs, and the posterior, we can predict new data. So it's often called D-rep, or replicated data. So the basic question is D-rep consistent with D-obs? If yes, then this model is a good description of the data. If not, then there's some inconsistency there. So we can quantify this using different ways, but one way that's recommended is we can calculate some test statistics. One popular choice is chi-square. We can calculate a chi-square from D-rep versus D-obs. And then if this p-value is small, then data is consistent with the model. And I'm running out of time here, if I may do a quick summary. So I start with describing that our experiment is basically looking at galaxies in the entire sky. And we calculate some summary statistics, for example, correlation function. And then we simulate many universes that's made of different, or that's determined by different cosmological parameters. And then we calculate summary statistics in those simulated universe. And then we interpolate those simulations and then we interpolate those simulations using something like Gaussian processes. And then we do Markov chain Monte Carlo to calculate the posterior. And then finally, we get our parameter constraints, and we can decide whether they are intentional with each other, where we need to look for more systematic errors, and whether there's any tension with each other, and whether general relativity is actually rolled in or rolled out.